Why is the ocean blue? Think about it. When you pour water into a glass, it looks perfectly clear, transparent. You can see right through it. But stand on a beach, look out at the horizon, and suddenly that same substance turns into a vast expanse of deep, brilliant blue. How can something that looks colorless in your hand transform into the color that defines our entire planet from space? The answer lies not in the sky reflecting off the surface, as many people believe, but inside the very structure of water molecules themselves. And once you understand it, you'll never look at the sea the same way again. Let's start with that common misconception: reflection. People often assume the ocean looks blue because it mirrors the color of the sky. It sounds logical. After all, the sea and the sky blend together at the horizon. But here's the test. If the ocean were simply a mirror, it would turn gray on cloudy days and black at night. Yet even then, water keeps a bluish tint, especially in deeper areas. So the sky may add a little extra hue, but it's not the true cause. The real explanation is more surprising, more fundamental, and it begins with how light interacts with matter. Light, as you know, is made of many colors blended together. White sunlight contains the full spectrum, from violet through blue, green, yellow, orange, all the way to red. Each color corresponds to a specific wavelength. Shorter wavelengths like blue and violet have higher energy. Longer wavelengths like red and orange carry lower energy. When light enters any material, be it glass, skin, or water, some wavelengths are absorbed while others pass through or scatter. That absorption pattern is what gives things their color. A leaf looks green because its molecules absorb red and blue light but reflect green. The ocean, it turns out, follows the same rule, but with a twist that involves the unique physics of H2O molecules. Water molecules are tiny, but they have a very particular way of interacting with light. They prefer to absorb longer wavelengths. That means when sunlight penetrates the water, the red, orange, and yellow parts of the spectrum get eaten up first. The deeper the light travels, the more of those colors vanish. What survives longest are the shorter wavelengths, blue and a bit of green. And because blue scatters more effectively inside water, it dominates what our eyes see. That's why shallow pools may appear turquoise while deep oceans look rich dark blue. The color is not painted on top. It's generated by the water itself, because of which wavelengths of light it lets through and which ones it swallows. Here's an analogy to make it crystal clear. Imagine a party where people of different energy levels are invited. The tired, low-energy guests, red and orange wavelengths, get stopped at the door. They never make it inside. The high-energy guests, blue and violet, slip through easily and dance in the center. The result? When you look at the crowd, all you see are the energetic blue dancers filling the space. That's exactly what's happening in the ocean. Water acts like a selective bouncer, filtering out low-energy colors and letting the high-energy ones shine. But there's a subtlety here. If water lets both blue and violet wavelengths through, why don't we see a violet ocean? The reason is in our eyes. Human vision is less sensitive to violet and much of it gets absorbed or scattered before reaching us. Meanwhile, blue hits the sweet spot of visibility and dominates our perception. So the ocean looks blue to us, not purple. This isn't just physics, it's also biology. The color of the ocean is a partnership between the properties of water and the design of our visual system. Now, let's think about scale. A glass of water looks clear because the path that light travels through it is so short. The molecules don't have enough distance to filter out much of the red and yellow. Your eye sees nearly the full spectrum, so the water appears transparent. But stretch that path to meters, then kilometers, as in a lake or an ocean, and the effect compounds dramatically. The longer the light travels through water, the more red it loses. What remains is that characteristic blue. This is why the same substance can look colorless in your hand, but turn into the planet's defining shade on a global scale. The key is depth. A teaspoon of water doesn't reveal the secret, but an ocean does. Here's another mind-bending thought. The blueness of Earth's oceans is not just an illusion. It's a direct expression of molecular vibrations. The way H2O molecules jiggle and bond determines which wavelengths they prefer to absorb. In fact, if you look closely enough, even a very thick tank of pure water, not seawater with algae or particles but distilled water, will appear faintly blue. That's because the color doesn't depend on impurities. It comes from water itself. The ocean is blue because water molecules are literally tuned to eat the warm colors and pass the cool ones. It's not poetry, it's physics at the molecular level. And yet, the story doesn't end there. The shade of blue you see in the ocean can shift dramatically depending on what else is in the water. Add tiny plankton, and suddenly the green part of the spectrum reflects more strongly, giving seas a turquoise or jade tint. Add suspended particles or sediment, and the water may turn brownish or gray as the scattering overpowers the absorption pattern. So the ocean's color is like a canvas where both physics and biology are painting together. Pure water gives the deep blue base. Life and particles add brushstrokes of green, teal, and even golden brown. It's an ever-changing masterpiece driven by both molecules and ecosystems. To put this into perspective, think about how astronauts describe Earth from orbit. They call it the blue marble, not because of the continents or the clouds, but because of the overwhelming color of its oceans. That blue is the fingerprint of H2O written on a planetary scale. Without it, Earth would not only look different, it would feel different. The color has shaped our culture, our language, even our symbols. We talk about the deep blue sea or feeling blue, all because water molecules absorb the right wavelengths to paint our world this way. Physics has literally seeped into poetry. Now pause and imagine what Earth would look like if water interacted with light differently. If H2O absorbed blue instead of red, our oceans would appear fiery red or coppery orange. From space, Earth wouldn't be the blue planet. It might look like Mars crossed with a sunset. Entire human cultures might have grown up associating the sea not with calmness and depth, but with heat and intensity. The very mood of our relationship with the ocean would be different. That's how fundamental this little quirk of molecular physics really is. It's not just about color. It's about how we imagine and experience our home. But there's an even deeper layer to this story. The ocean's blueness is not just a visual quirk. It's tied to the physics of why Earth itself looks the way it does from space. When astronauts say they're struck by the blue marble view, they're not exaggerating. The oceans cover over 70% of Earth's surface, and their molecular filtering of sunlight is what paints the planet blue. Without this effect, our planet might not have the same symbolic identity it holds today. Imagine the cultural ripple of that change. No blue planet, no blue in countless flags, no psychological association of blue with calmness and depth. A tiny quirk of physics didn't just color the oceans, it colored human imagination. Let's add one more analogy to drive it home. Think of a stained glass window in a cathedral. The glass itself is clear when thin, but add thickness, and suddenly colors emerge as certain wavelengths are filtered out. The thicker the glass, the stronger the color. That's the ocean. A glass of water is like a thin pane, colorless. The sea is like a wall of stained glass kilometers thick, filtering out reds and oranges until only blue shines through. The difference is that nature built the filter at a planetary scale, and it works not by artifice but by molecular resonance. Now, here's the moment of Eureka. The ocean is blue not because of the sky above, but because of the physics inside every single water molecule. H2O isn't just the substance of life. It's also a hidden artist, painting Earth with a brush made of light itself. The bonds between hydrogen and oxygen vibrate in such a way that they absorb warm wavelengths and pass cool ones. That vibration, invisible to us, sets the stage for everything we see when we look out at the horizon. It's humbling to realize that something so basic, so universal, shapes the very image of our world. And here's where the practical value comes in. Once you understand how water colors the ocean, you can see connections everywhere. Scientists use subtle shifts in ocean color, measured from satellites, to track algae blooms, monitor climate change, and even predict fish populations. Because color is not just beauty, it's data. The same physics that makes the ocean blue also lets us use it as a global sensor. By watching the shades of blue and green, we gain insights into the health of ecosystems and the changing balance of our planet. The ocean's color is more than aesthetic. It's an early warning system, a record of life, and a diagnostic tool for the Earth itself. So, next time you stand at the shore and look at that vast expanse of blue, remember, you're not just seeing a reflection. You're witnessing physics in action. You're seeing how molecules shape color, how depth amplifies it, and how biology can tweak it. You're looking at a story that begins with the tiniest bonds between atoms and ends with the entire identity of a planet. That realization alone is worth a pause of awe. The sea is blue not because of poetry, but because of precise rules of physics, and yet somehow that makes it even more poetic. And that's what makes science so exciting. It takes something ordinary, a glass of clear water, and shows how, on the scale of an ocean, it becomes extraordinary. That shift in perspective is a key, and once you hold it, you start unlocking hidden truths all around you. If this gave you that sense of awe, that spark of curiosity, then you're in exactly the right place. Because here on How It Actually Works, we take those everyday mysteries and reveal the science that transforms them. So give this video a like, share it with someone who's ever wondered about the color of the sea, and subscribe to how it actually works. Together, we'll keep collecting keys to curiosity, unlocking the beauty of the invisible rules that shape our world.